So imagine that these are two traveling waves. Clearly they have different characteristics. I want you to try to answer this question. Which is traveling with the greatest speed? I'll give you a little bit of time to think about that. All right, how'd you do? To be honest, this is a trick question. You don't have enough information to be able to answer this question. These are the same two waves I just showed you. If they're both traveling waves, then they should be moving. A still photo like that will never show you the motion. So to help with that, this is an animation. I'm using the website Desmos. If you've ever tried that, it's pretty handy. It gives me the ability to animate the wave, and that will allow you to easily see which wave is traveling faster. Like clearly, the lower one is traveling at a much faster speed than the upper one. Without seeing that, though, there wasn't an easy way for you to figure that out. In fact, with the information I gave you in this slide, you can't figure that out. Fortunately, though, there is a way to figure out the wave speed without the need to actually see it in motion. The speed of a wave, or the wave speed, is equal to the wavelength multiplied by the frequency. So if you know those two values, it's actually not too hard to figure out what the wave speed is. I'll give you an example. What is the speed of a water wave with a 1.5 meter wavelength and a frequency of 6 hertz? Well, we have our relationship, we just need to plug in our numbers. So the wavelength was 1.5 meters, the frequency was 6 hertz. Remember, that's the same thing as inverse seconds. So mathematically, that's just 9 meters per second. This is the unit of wave speed in standard units, so it works out pretty easily. Comparing wave speeds is not hard, you just need to know wavelength and frequency. Here's those two waves again. I know in the animation I showed that they didn't have the same speed, but just forget that. Let's say that I adjusted them, so now we know for sure that they have the same speed. So if they have the same speed, which I'm saying they do now, which has greater frequency and which has a longer period? Can we figure that out just by looking at the figures? I'll give you a little time to think about that. In this case, yes, we can. If we know that they have the same speed, then we have everything we need to answer this question. The same speed means that they will cover the same amount of distance in the same amount of time. So by the time the wave travels this distance, it will be the same amount of time that this wave travels this amount of distance. In that amount of distance, the top wave has more oscillations in that distance, which is like saying it has more oscillations in the same amount of time. So this top one clearly has the greater frequency. More oscillations in the same distance is the same as saying more oscillations in the same amount of time if you know they have the same speed. Okay, that would mean the lower one has less frequency. To answer the second question about the period, we need to remember how period and frequency relate, and the key is that they're inversely related. So the greater frequency is a bigger number that I'm putting into the denominator. Mathematically, that works out to give me a smaller total result. So the one with the greater frequency will have the shorter period. The one with the smaller or less frequency will have the longer period. Another thing I want to look at is, remember, wave speed is defined as the wavelength multiplied by the frequency. I said that we're now assuming they have the same speed. from this relationship, we can define the wavelength as the wave speed divided by the frequency. Just did a little bit of algebra over here. So if we want to compare wavelengths, now visually that's easy enough to do. We can see that the bottom one has a longer wavelength than the shorter one. But we can also do it with our relationship between wave speed and frequency. Because frequency is now in the denominator when defining wavelength, that says that for two waves with the same speed, this thing, that wavelength and frequency are also inversely related, a lot like frequency and period were. So that means that the one with the greater frequency has to have the smaller wavelength. Now that's assuming that they have the same speed, which we are. If one has less frequency, then that's going to give it a larger wavelength. So visually it was easy enough to see that, but you don't always have a nice picture of the wave. Sometimes you just have numbers to work with. So it's useful to understand this inverse relationship between frequency and wavelength when dealing with things like wave speeds. The reason why I'm telling you this is that in your life, there's a lot of waves that you interact with all the time that have the same wave speed. So by knowing that if those waves have the same wave speed, that frequency and wavelength are just inversely related can lead to a lot of useful understanding. We'll get to that topic later when we discuss chapter 26. The last thing I want to go over is the different wave mechanics. So this is physically how the waves operate. I've been showing you really just one example until now. That's known as a transverse wave, where you have a wave on a string is a good example of that. The key to a transverse wave is that if your wave motion, let's say, is horizontal here, moving to the right, a transverse wave has individual particle motion that is perpendicular to that, transverse. So we can define a transverse wave as when the oscillation motion is perpendicular to the wave direction of travel. The second type that I want to consider are known as longitudinal waves. And I haven't really shown you an example of this yet, so this might not make sense. Think of this as a slinky, a metal slinky, if you know what that is. If you don't, I'll show you a video of that real quick. But with a slinky, you can stretch it and push it back and forth like this. That's going to send a wave horizontal again, so same direction as our transverse, just horizontal to the right. But in that case, your particle motion or your oscillation motion is going to be parallel. So the key to longitudinal waves is that the oscillation motion is parallel to the wave direction of travel. Here's an actual animation to maybe visualize that better. So up here for transverse, our wave motion is to the right. But if we look at the actual point of the string, it's just going up, down, up, down. Its motion is perpendicular. Okay, for the slinky here, when they compress it, you can see the energy transportation. Remember, a wave is just a transfer of energy. It's the energy that's actually moving in a traveling wave. If that motion is still horizontal to the right, but your particle motion is parallel, that's what we call a longitudinal wave. So it's this parallel versus perpendicular that's the key to defining transverse versus longitudinal. I mentioned I'd show a video. You need to at least see this at one point. And since we can't meet in person, I found a quick little YouTube example. If you have a slinky, you should actually try this. It's kind of mesmerizing for some reason. Okay, I think that's good enough for that. Here's one last animation to help visualize that. I wanted to emphasize again that for transverse waves, if we have a wave on a string here, if we look at an individual particle, the particle isn't going anywhere. The net motion is 0. So what's actually moving in a traveling wave is not the medium, it's not the particles. Remember, it's the energy. It's the same thing for longitudinal waves. If we track an individual particle, it's moving back and forth parallel to the wave direction, but the net motion is still 0. These particles aren't actually going anywhere in the grand scheme of things. So it's the energy that's traveling. So what you can think of for this example is think of this as a gas, and then you have a piston that's simply compressing the gas. So right there is a compression. And that creates this pulse of high pressure in the gas. And then you get an area of low pressure and then high pressure. So longitudinal waves are often called pressure waves. They're also often called compression waves because you had to compress it to get the pressure difference in the first place. Let's go through a couple of real-life examples of each of these. I've showed you a lot of strings for transverse waves, so hopefully it's pretty clear that on a musical instrument that uses strings like a guitar, when you pluck the string, you're creating transverse waves. Interestingly, though, for musical instruments, it's not really that initial transverse wave that you create that causes the sound. It's the combination of multiple transverse waves that result in what are called standing waves. And that's what musical instruments are based on. We'll get to standing waves later. I already showed you the ocean waves. Those are examples of transverse waves on the surface. Another big one are electromagnetic waves, and that's of course all types of light. So visible light, infrared light, gamma rays. We'll get into that in chapter 26, like I mentioned earlier. For longitudinal waves, I'll go ahead and give you an example. Here is your example. Okay, it's right here. If you're having trouble seeing this, it's not your computer because this is your example. My voice is the example of a longitudinal wave. Sound is probably the most well-known example of longitudinal wave. I didn't really know how to visually show sound, so here I just have some volume meter. This animation I showed you is actually a good representation of sound. So if you think of this as just air, this would just be a speaker. If you've ever taken a speaker apart, it's just a plunger that's able to move back and forth. The only real difference between this animation and a real speaker is that this plunger is moving really, really fast. So when it pushes out, it compresses the air that's right next to it. And that sends out a pulse of energy or a high pressure in the air. And then you get an area of low pressure right behind it that emanates outward from the speaker. Eventually this can enter your ear, and that change in pressure causes your eardrum to vibrate back and forth at the same frequency as the vibration of the speaker. That's why you hear exactly what comes out of the speaker. This brings us up to another good point. When you're dealing with sound, frequency is commonly known as pitch. So if you've heard that word pitch before, it's just another way of saying frequency. It's usually reserved for sound waves. The other thing I want to mention takes us back to that original simulation. When I was shaking this wrench, I was creating a wave with a certain frequency. What you might be able to see is that the frequency of my wave is actually equal to the frequency with which I'm shaking the end of this wrench. And that's an important observation to make. The wave frequency is always the same as the source vibration frequency. So whatever your repetitive motion is whatever frequency that has, that will be the same frequency as the wave that's generated. You can see a little more smoothness when I have an automated system do it. You can see if I increase the frequency of the wave, it gets closer, the peaks get closer together, but really what happened is the source here started oscillating back and forth faster. As I slowed down, clearly the frequency of the wave's gone down, but it exactly matches the new frequency of my source here. Okay, so the frequency of your wave is always the same as the frequency of your source. My last example includes both longitudinal and transverse waves, and that's earthquakes. So earthquakes, if you haven't learned about these before, they involve both types of these waves. This top one here is commonly referred to as a P wave. You can see that the wave motion here is to the right. The particle motion is back and forth to the right and left, so this would be a longitudinal wave up here. Longitudinal. Down here, in earthquakes, you can also get examples of transverse waves, where the wave motion is to the right again, but the particle motion is perpendicular, or up and down. Those are known as S waves. I've heard several different explanations for what S wave means and what P wave means. Some have been, this is a pressure wave, or one was a push-pull. Really, the one I like the best is P is known as primary wave. And the reason why that makes sense is because it's in comparison to S, which is secondary wave. So primary waves travel faster, so they get there first. Secondary waves come in later, so they're secondary. Now, what the exact meaning of that is, I don't really care because we're not a geology class. What I actually want to ask is, which type causes the most damage? Which one do you think is the worst for damage? Well, if you look at this, if you're this building here, vibration back and forth like this could be annoying and could certainly lead to damage, but if your building is rocking up and down like this, that's when you're really going to start to cause problems. So it's this secondary or this transverse wave in earthquakes that cause the most damage. I think that's a pretty good introduction to waves. We've gone over several basic wave characteristics. Good understanding of those characteristics are going to be crucial if you really want to understand concepts like sound and light.